Yes. All right. Well, it's a great pleasure to be able to talk to everyone, and thank you very much for including me. That's super. What I want to do is talk about work that we started in like 17 years ago with DOE funding, the Department of Energy. They used to fund ocean carbon studies. That development continued through Ken Bissler's Vertigo program. And then in 2007, we finally made the first light with the device which I'll call the Carbon Flux Explorer, which is an imaging optical sedimentation recorder. That helped. A lot of people helped. And Michael Fong and Todd Wood are fundamental in terms of the topic that I'm going to talk about, which is our deployments of this device in the California coastal environment, particularly in the Santa Cruz Basin. And what we found was something that was really surprising to me, was that at a time that we least expected a high sedimentation event, we found a really high sedimentation event. And that took me like 3 years of head scratching to figure out. And eventually, thanks to a number of other people who've helped me think this through, and also Meg. Where's Meg? Meg? Yes, Meg Estapa has contributed to this paper in many ways and made it much better. So what's the game? So a lot of people are focusing on looking at the dissolved pools of nutrients and getting at the carbon cycle that way. And my focus has been looking at the particles directly. And the fundamental motivation is that if you do the math in terms of global photosynthesis and the biomass of standing phytoplankton, everything in phytoplankton gets eaten once a week. Therefore, it's a ridiculous prospect to follow this from shipboard studies unless you're doing a process experiment such as proposed in export. But you can't do that forever. So that got me motivated to start working on developing a device that is float-based that would follow sedimentation and particle dynamics. And the major question is, this diagram is drawn as a steady state, and the question is it in balance? The numbers in this diagram, the 10, we've already heard, are uncertain between 4 and 12 and a half. And the other question is, there's a temporal domain to those assessments, where some of the lower assessments are coming up in later years based on new geochemical methods. And so the real question is, and some of the higher ones are based on nutrient proxies and inversion through physical models. So the question is the biological carbon pump already changing and we just haven't been able to observe it? Or is there a methodological issue? And I don't know the answer, but it's really important. So the fundamental question is, both particle concentration and particle flux are important indicators of how the food web operates. Just think of going through the garbage cans in Manhattan. You can tell who's living where. This is a prototyping platform for the second variant of our Carbon Explorer, which is a float that carries transmissometer sensors of the kind that Meg has been deploying. Also, a new sensor for particulate and organic carbon. And I've talked about this over and over, but the major point is that it shines a beam of polarized light through a laser, through a polarizer, and then down at the end of the beam, there's a polarizer rotated at 90 degrees that blocks the primary beam. And the idea is that carbonate particles are birefringent, therefore they depolarize the plane of polarization of the beam, and therefore those photons pass to the detector. The reason that this sensor hasn't leapt into availability is the fact that there's a big job involved in keeping 1,000,000-to-1 crossing efficiency polarizers crossed in a profiling mode. Wet Labs is about done with this problem now, and we're taking it out to sea in 2 weeks. So the focus of this talk is not on the particle concentrations, but on particle flux. And Scott Doney already introduced the topic of the remineralization length scales, and of course it's embedded in Ken Bissler's Philip Boyd. So this is the device that we started developing in 2000, and it's finally propagated onto a float in 2007, and this is its present variant. So to the left is a standard Argo float. It happens to be the one provided by Scripps. And on the right is a device that I call the optical sedimentation recorder. And it has components which include a very high aspect ratio funnel, a downlight, an imaging stage, and down here there's an imager that looks straight up at the particles on this image plane. So there are three modes of imaging. One of them is a dark field illuminator. Light shines in from the side. You can actually see the color of the particles. Then there's a downlight that shines light through the sample, and whatever gets to the camera is a transmission-based measurement. And then, as in the polarizer outfitted transmissometer, we do exactly the same thing. There's a polarizer on this downlight. There's a polarizer rotator in front of the camera with another polarizer. When the polarizers are parallel, you get the transmitted light image. When they're crossed, you see black, unless there happen to be carbonate organisms. So transmitted light for a transmissometer leads to the property that everyone uses, which is beam attenuation coefficient. And there have been a number of papers published in the literature about how it's quite an excellent proxy for particulate organic concentration. For particles sitting in a layer on a piece of glass, the equivalent optical property is called attenuance, which is the log of the light loss through the sample. But of course, there's nothing in the way of path length that you can know about, because it's just a thin, unknown layer of particles. So the property is attenuance. It's derived from transmission. And if you change, basically, this device operates in time steps of hours, takes image sets, and then you can see the buildup of particles on the stage. Eventually, that stage is cleaned, and you start all over again. So what you watch is the increase in sample load with time. And then if you know each time step and sample load increase, you can turn that into a flux. And the units are in milli-attenuance units, centimeters squared, which is the optical volume of particles on the sample stage, normalized by the trap opening, normalized by the time deployed. And then there's birefringence, which is the cross-polarized photon yield. We have the light source as the reference. When the polarizers are crossed, in order to get a certain count on the imager, we have to adjust the shutter speed of the imager. So this birefringence or photon yield is calculated in absolute terms using the light source as the reference. And of course, it turns up when carbonate shells are present in the sample, they light up. And similarly, that flux unit, this is a physically valid parameter. It's independent of the method that was used to generate it, is parts per million centimeters squared, centimeters per -2 per day. And then dark field, we don't have an absolute calibration of it, but we can actually see the color of particles. So here's an example of a raw image of particles. This is a sample after a cleaning sometime after cleaning. This is the cleaning image of the clean stage. These are millimeter dashes. So you simply divide that by that, and you get transmission, and it flattens the image, and then you take the log, and you get attenuance. And this is the image of attenuance image of that particle. And we can resolve about 15 microns, and the diameter across this is 2.5 centimeters. So cross-polarization, you can immediately see little dots light up, and these are foraminifera. This is actually a living Spinos foraminifera. There are several of them in the sample associated with aggregates. That's a pteropod shell. Those are all forams. There's a haze in aggregates that we can account for in coccoliths. And this is the dark field image. And so you can actually discern the color of particles in a way that you can't get with the transmitted light image. And that could be very diagnostic in identifying specific particles. So our study site is in the Santa Cruz Basin, and there were moored sediment trap deployments in other years here. And just to put you on the world map. Is my time up? Almost. Okay. So the Carbon Flux Explorer is deployed. We did several cruises in three different seasons. One was May 2012, January 2013, and March 2013. These are all development cruises. We weren't intending to do science. And this is the mission of the Carbon Flux Explorer. And the idea is that you take an image, and every 0.4 of an hour, you keep on taking images. And then eventually, after about 2 hours, you clean off the sample stage and go again. And surfacing every 8 hours, and then go to the next depth. And I'm going to show you some animations. About 1 second of animation is about 2 hours elapsed in this device's record. So one of the questions is, how do we relate remotely sensed properties, such as chlorophyll? And by the way, this is the dark field illumination, and you can actually see the color of aggregates in 2 different seasons. And to me, this was an astonishing result. I had gone out in January expecting to get nothing because the biomass was low, and my gosh, the entire water column was raining particles. And the answer, which should have popped up, is, does surface chlorophyll allow you to predict flux? The answer is not simply. So these are the raw data from the Carbon Flux Explorer at 144 meters, the ramping up of sample load, cleaning, et cetera, et cetera. We've run these things for 40 days, and they don't biofoul, so that's encouraging. These are short deployments. And so, again, the attenuance flux is the time derivative of the change in sample load divided by times the sediment, the stage area divided by the trap area divided by time. And this is the flux for January high, March intermediate, and May low. And then this is the PIC flux, and it's guts. And there are a few cases where this is a birefringent particle. It's huge. It turned out that it dominated the sample there. I took it out of the averaging, but it's actually a real sedimented particle. It's a carapace of the zooplankton. And then there are a few spots here where cyprid barnacle larvae that had calcified were swimming around in the sample, and we weren't able to correct for that in the data processing. So here's the chlorophyll time series, May, January, and March. We're going out in August this year to see if we can get a low. On the left, this is the satellite retrieved chlorophyll. The open bars are the week before the cruise. The closed bar is the week during the cruise. And for POC, these are the retrievals from the Modus Aqua platform. And then the shaded bar is the in situ estimate of POC from transmissometry. So by all metrics, this was low biomass, and these later were high. And you can see the transmissometer profiles there. So how did particle flux look? Totally in reverse, as you would have guessed. Low biomass, high flux. And not just a little bit high, it was about a factor of 20 higher than in the other season. How did PIC flux vary? The PIC flux was high, again in January. And a very interesting factor of these data is that when you try to relate these data to remote sense biomass, it doesn't really help you come to the answer of predicting sedimentation. You need to know something more about the system that's the ecosystem, the communities. One of the other things is that when these large aggregates were present, the variability of flux was much lower. So when large aggregates were abundant in the water column, we had very little variability. We tried to calibrate these samples using surface tethered optical sedimentation recorders. The answer is it failed because we discovered a hydrodynamic effect that was not insignificant. And it's just pictorially illustrated here. Here's the Carbon Flux Explorer image, and here's the image of material collected from the buoy. Here are the size distributions of particles sampled with the Carbon Flux Explorer. Here's the size distribution of particles sampled with this surface tethered instrument at the same depth. And one of the interesting things is, and we had ADCP data, acoustic Doppler current profiler data, and so we were able to calculate the rate of flow of water across the top of the trap. And the buoy saw little material greater than 2 millimeters in size, except when currents dropped below a centimeter a second. And they went up to about 7 centimeters a second across the trap. So let's start winding up. So high surface chlorophyll does not imply high surface sediment, high sedimentation, or high carbon export. Low chlorophyll suggests that there was a strongly grazing ecosystem. And if you invert that, you say if there's a bloom, it's kind of like how many Brussels sprouts can I eat? Now, most carbonate is calcite in the study area from Florams and Coccolus, and but we had a short deployment of these things several months later at Station Papa, and the carbonate was all dominated by aragonite and pteropods. We observed a mass reproduction event of Cleopteropods at 150 meters in one of these instruments. I have movies that I can show, maybe in movie night tomorrow night. So for the coastal zone in the California, POC flux, so if our results map to surface tethered sediment traps, then based on particle size distribution and attenuants loading, the minimum volume of underestimated flux is a factor of 3, and in the case of January was a factor of 20. We hadn't expected that. We were depending on this surface tethered instrument for our calibration samples. The other thing is that the January 2013 rates exceeded the highest trap flux measured in the San Pedro Basin or the Santa Barbara Basin in other years. And there is a challenge for continuous observations. Like, we can put a Lagrangian instrument and get great results, but in a week it's gone from the area that you want to study. So how do you actually maintain a presence in an active coastal environment that you wish to do, because you require a Lagrangian framework for your observations? And that suggests that either cooperative autonomy, where you have a Lagrangian device like ours get rescued by underwater AUV that latches on it and pushes it back to where it ought to be operating, or actually cutting off the end of Charlie Erickson's glider and embedding our instrument in its tail, and that would work, and actually use the glider as a profiling, as an optical sedimentation recorder, and then have it go navigate back to the location. Those are doable. Engineering takes place. So what's next for the Carbon Flex Explorer? We're going out on the Oceanus. Remember that boat? I saw that boat delivered and at Woods Hole. And we're going to be collecting we've moved the sample collector over to the float. And this is a cool thing, rapid prototyper part that looks like the nose of the Starship Enterprise. We expect to have the image analysis running on the float. Mission capability is 8 months at hourly frequency. Pending detection of living organisms. There are swimmers, and we know how to do that. You just need to get funding. Onboard size analysis. Hannah Bourne has a poster where she's exploring how we're going to do that. And yes. And then obvious, merge the particle concentration optics with the flux optics on the same platform. That's easy. We already know how to do that. But also the candidate sensors that the biogeochemical floats, such as pH, look really interesting. Oxygen is an obvious one. And then we can, yeah. Okay, so that's the carbon cycle. Stability of the biological carbon pump is not known, but can be known. Thank you. Break.